Good afternoon. My name is James McGivern, and I'm going to do a talk on JUnit PowerUp. JUnit is probably one of the most popular Java testing tools out there. But before we start talking about that, a bit about me. So I work for Cisco. I work in their web security department. So we deal with basically providing a secure web proxy. Billions of requests a day, equal to that about of Google. So we do a lot of multi-threaded applications, and obviously there's a lot of problems with testing those, and I'm going to try and give you some of the tools and ideas that have helped us test our code. I like cats and I hate Marmite, so don't put Marmite on a cat and give it to me. This is the white elephant in the room, JUnit versus TestNG. I don't care. Use whichever one you like. They are pretty much identical. Give or take a bit of syntax here and there, and a few other things. Most of what I'm going to talk about is applicable to TestNG, just as it is to JUnit. So, one busy morning, we find ourselves wondering about concurrency. Basically, concurrency is stuff happening all at the same time. It might be done in coordination, there might be no coordination, and as you can see, it's also got some extra meanings that we just don't care about. So, when we have a single-threaded application, we know exactly what's going to happen at any point in time because we know where the current point is and we know what the next line of code is going to execute is. Once we've got multi-threaded applications, that means we've got multiple threads, executions, processes, at different points in the application. And it doesn't go thread 1, thread 2, thread 3, thread 4. It might go 1, 1, 1, 4, 2, 1, 3, 3, 3. And so you don't know with a great deal of certainty what the next line of code to be executed is. But we are computer programmers. We know that underneath it all, there is an algorithm determining what happens next. So although it might appear stochastic or non-deterministic, it's not really, unless you're doing something really funky with random number generation or something like that. So when we have all these threads acting in unison in one application, we have tons of new problems to worry about that we didn't have to with a single-threaded application. Deadlocks, which are when two people are basically holding on to something, pulling in opposite directions, and neither will let go. No one wins. It's a tug of war. Starvation, you know, we've all been working on some network somewhere and trying to watch a YouTube video, and suddenly the whole thing ops and carries on for a bit, and that's starving the network. The other ones, race conditions and contention, we will cover a bit more detail later. But why is multi-threaded code such a problem? It's really simple. Everyone should recognize this pattern. It is one of the oldest patterns in Java. It gets covered in every book, and it's mostly, well, hated by most people nowadays. But if we have two threads, A and B, and they are somewhere else in the application at the moment, and they're both just about to come into this method, and we'll have a look at what happens. So thread A enters the method, and is followed by thread B. And then thread A goes, is it a null? Next time, thread B goes, is it null? Both of those are going to equate to true, false. So thread A goes, right, so let's make a new singleton. That sounds fair enough. But then thread B comes in straight after and goes, let's create a new singleton. So the first value that A created has just been overwritten by B. Now, when A returns, it's actually going to return what B just created. So the whole thing's a mess. What's going on? Each statement is an atomic block. That means that piece of code will either be executed or it won't. There's no halfway execution about it. Every thread, when it has its turn, executes at least one atomic block. As I said before, it might do 3 or 4 in a go. The threads take turns, but order's not guaranteed. Well, again, there is a bit of a guarantee in the order, but if you understand the algorithm, well, who does? Who wants to? Who needs to? But the problem is that given some number of threads, T, and some number of statements, S, the number of possible ways that that code could be executed is given by this really crazy equation. So the exclamation mark, that's a factorial. So 3 factorial would be 3 times 2 times 1, which is 6. 4 would be 24. See, it gets bigger and bigger and bigger, much faster than an exponential function does. And then underneath, we just take off all those ones that we know are the same. So basically, we're removing duplicates, and those are the unique orderings we have left. As you can see, 2 threads, not a problem. 3 threads, getting a bit more tricky. 100 threads? You now see how many combinations and how many different ways of executing this code there is. So, what can we do? Well, the first thing we can do is we can write good unit tests. Fibonacci sequence, very famous mathematical sequence, and this is the specification and tests that say how it works. No threading here at all. This is just a good example of a unit test. What is the point of writing unit tests or any other tests, though? Well, obviously, for TDD, it's part of the practice, and it creates this living specification of how your application works. And you've probably heard that a lot of times, and it's a lie. The cake is a lie. What's actually happening is that you've got an executable specification for X% of your application. And there are some things that you have not tested, either on purpose or because you didn't realize, or there might even be emergent behavior that you're not aware of and therefore can't test either. So no amount of testing, manual, automated, will find all the bugs. It's just a fact of life we have to live with. But we have limited time, and we have to ship stuff. So we have to make sure that when we write tests, they are worth writing. A lot of unit tests are worth writing. A lot of multi-threaded tests aren't. And the reason for that is because multi-threaded tests take up a lot of time to write, they take a lot of time to maintain, and writing them just for the sake of writing them doesn't give you much. You're better off investing your time in the single-threaded code, making sure that works exactly as you expect, and then when problems occur or when you anticipate a problem in a particular area, target it with multi-threaded tests. So JUnit comes with a bunch of runners, and a runner alters how the tests in a particular class get executed. They've got suite runners, which allow you to group tests together into little collections, like you might have a UI suite, and you might have a database suite, and so on. Or we have parameterized, where you can say, I want you to test this function with these values, A, B, C, and D. Theories, categories, and enclosed have been done excellently in a JUnit talk last year. So that's on parlays, and I'm not going to bother covering it now. Third-party ones, you probably come across the Mockito, EasyMock, PowerMock, custom ones, JBehave, Spock. Spock is really a good example. It's running groovy. It doesn't look like a JUnit test. You write it completely differently. In the background, it's just a JUnit runner. So they are powerful. They have a rather big interface with not much helpful stuff on it. So the get description of the runner says, I will describe everything I am about to execute. Run gets called by JUnit, passes in the run notifier. As run goes through the tests, it will let JUnit know which one's passed and failed and so on. And it does this using the run notifier. And you just say, this test started, this test failed, this one didn't run, this one had an assumption at the beginning that failed, so it's not a failed assertion, it's a failed assumption. And then the description, again, it's just a basic Java thing to help you build up that little tree that you see when you're running it in your IDE. So if you're going to implement a runner, you need to implement those features. However, runners affect the entire test class. There's no real discrimination about it. Even when you're building on the top of existing runners, you often find there's a lot of complex code and a lot of boilerplate you need to do. And the final, most annoying one that most people have run up against in their life at some point, especially if you've been doing this for a couple of years, when JUnit was younger, is that you can't stack these runners. So if you want to run some Mockito stuff and some Spring stuff at the same time, you're out of luck. So we have rules instead. Rules can interact with individual tests. They are basically like temporary resources. You can apply them to a method or to a class. Here's a little example of the Mockito rule. So you can see how little code you need to implement in order to get a test rule running. Now that we've covered some JUnit basics, it's time to look at what happens when we're running some threaded code. This lovely section of code is actually from a friend of mine, Peter Lowry. He writes the Vanilla Java blog. And basically, we have this volatile int class. It's kind of like the atomic ints and atomic boolean, but is volatile instead of atomic. And then we've got some test should increment counter. And we start it off with 32,000 that we have to loop around. And that's going to be done by 64 threads. Each thread is a new executor. It's either a new executor, it does this loop of adding up, and then it just returns. And they all shut down. Now, what you'll find is that this code as it stands will run and pass. No problems whatsoever. However, if we change it from 32,000 to, say, 100,000, suddenly errors will start appearing. And those errors are that you get lower counts for a particular thread than you expect. Instead of getting 100,000, you'll get 70,000 or lower. And the reason why is because of the multi-threaded interleaving and the way that volatile works in multi-threaded applications. So your test was passing, but in reality it might have failed. So you have to remember that just because you've multi-threaded tested your code, it doesn't mean it's actually going to work under the real-life conditions. So you have to know your stuff. You have to know what's going on. You have to understand it, and the only way of doing that is by reading. These are some of the best books that I've come across on this subject. Of course, Brian's here this week. I think Venkat might be here, but I'm not sure. His is the latest book, so it's the most up-to-date, especially with some of the more modern Java enhancements. I recommend that you read them back to front. And front to back as well, because that's probably easier. So, what type of stuff is going on? Sorry. So, this is a picture of the MapReduce algorithm. It might not look like it, but what we've got at the top is we've got a bunch of caterpillars. And we're going to map those caterpillars onto a butterfly. So that's that first step where you see 4 caterpillars turning into 4 butterflies. And note that the butterflies are different. They've got different shapes on their wings. One of them's a bit frowny, maybe even a bit vampire-y. So once we've converted them into butterflies, we combine the first 2. So that's your first reduce. And you'll notice that that butterfly's got 2 different spots. And we keep going down until the end. Now, why this is important is because what this is where threads only need to coordinate at the end of the task. Once the job has been split up at the beginning, there needs to be very little coordination between the threads. So, what we need to do is we need to find a way of, when we're testing this stuff, making sure that we are weighting an appropriate manner, or not doing something horrible by modifying our code simply to make it testable. So a weightility, awesome library, simple DSL, gets rid of all this horrible stuff you see in tests sometimes, like while so-and-so thread sleep 1000 and cross your fingers. Now you've got a really nice DSL. So you say await until this thing, this callable, returns true. It's not that clean though. What you'd really like is to write it like this. So instead of having this callable, we have size of, which is a callable. It's reusable. You can use it on any collection. We can now say, wait until any collection is of size X. Really good, really reusable. But can we do better? So, what if we just wrote this first line? So this copies the Mockito idea where you do given so-and-so dot thing will return, same idea. So we just say, wait until the call to method, this repository size is equal to 3. It's nice and readable, really simple. Do it using reflection. We want to check a particular field. It could even be a private field. We don't have to modify the code. We don't have to crack out any reflection library. It just does it for us. And then sometimes we need to poll. And so it has a much more advanced feature where you can say, with this poll interval of 100 milliseconds and poll delay at the beginning of 20 milliseconds, wait until this thing's true. So it's a really nice DSL for making assertions about tasks that happen asynchronously. The next problem we face is shared resources. Shared resources result in race conditions. Race conditions are where I'm trying to put something in the pigeonhole, you're trying to put something in the pigeonhole, and the first person gets it in, and the second person loses out. And it also has problems when you're doing stuff like this counterclass. So you can see here, depending on the ordering of execution, it could be that value is increased, count is increased before the value has been added, and so you end up with this situation where the sum isn't what you would expect anymore. We fix that by another tool, Threadweaver. So this is a Threadweaver test. We say at threaded before. This is the same as at setup or at before. And basically, we just create our hash map in this. We've got threaded main. This is the primary thread. Number one, it will execute first. And it's just going to put something in the map. The second thread, threaded secondary, happens after the first. And then obviously thread after happens at the end. So you now have a really simple way of breaking up the interactions of two threads on a particular resource and making sure that certain actions happen at certain times. It is a little bit dodgy at the moment because it appears as if the project is somewhat inactive. There have been releases, they're still updating the forums and the bug trackers, but there haven't been any releases and there hasn't been a great deal of activity on the repository recently. Doesn't matter, works as it does. And we just wire it into a JUnit test like this. It'll do the usual assertion fails and yeah, it's a nice supplement to JUnit when you don't need too much power and it's quite simple to use. It does actually have some really powerful features, but I think they're quite awkward to use, and if I was going to do that type of stuff, I'll use one of the tools that I've got later on. So, we are at Princess Protection HQ, and what we have is a group of processes. They might be on different machines, but let's just assume for now they're on one machine. And you've got some of them which are inputs. A and D. And K is the output node. And you'll notice that C actually feeds back up into A. So the data comes in, it gets some processing done, and then some of that's fed back into A. It's called a recurrent network. And this allows you to do some really cool stuff. But when you need to test it, you're in for trouble. So the first library that most people will all turn to is Java Pathfinder, created by NASA. You know, it's got to be good. They sent someone into space. However, it is difficult to use. Doesn't integrate very well with JUnit or TestNG or Maven. So it's certainly worth checking out, but it wouldn't be my first choice. This is Byteman. I think it's from JBoss still, and basically what it is it's a way of manipulating bytecode at runtime. It's not that dissimilar to AOPs like Aspect J, but it's actually far more subtle in the way that it works. And it's got less constraints on it, like it doesn't need to have empty constructors and all these things that you've probably encountered with Spring Aspect J. So, what can it do apart from, the stuff we've seen already from the other tools? Well, one of the things it adds on over just plain old AOP is it's much easier to write code for. And the reason why is because everything has this pattern, event, binding, condition, action. And we'll have a quick look at some code because it makes it even more easy. So this is how I fault inject into a service that we're testing. So you can see here, there's a rule name, and it says, let's target the executor interface. So every implementation of the executor interface is going to have this applied to it. We're going to target the execute method, and when something enters the execute method, if it happens to be coming from this class and that method, we're going to throw an exception and trace that, and do some tracing to the stack. It's dead easy to introduce faults that way. In fact, I'd say it's almost easier to do it this way than it is to do something like Mockito, where you have to do the whole throw, when, so and so. No, don't bother with mocks. Just make the code actually do it. It's got a bunch of built-in stuff that you will find useful. And what's even better is that you can extend it and write your own helpers and just use them straight in your own code. It integrates brilliantly with JUnit. As you can see here, we've got the script that it's running. You can even apply a specific rule to a specific class. It's so powerful. It's beautiful. And it's, like I said, it's much simpler to work with that than any other AOP-style language I've come across. But this is not the end. There are more tools. Concurrent unit. It's quite a popular add-on library. I'm not that fond of it. A lot of people do like it though. So if you want to check it out, I'd recommend it. Yeah, I'd recommend it. It's worth checking out, but for me personally, it doesn't fit with my style of testing. Find Bugs does have stuff in there. If you are running a Maven build, if you're running a Jenkins service or anything like that, you should be doing this type of stuff automatically on every check-in because it costs you nothing and the rewards are worth it. Freud. It's a fairly new one. It's spun out of LMAX, who did the Disruptor a couple of years ago. And this is essentially, it's a DSL for describing check style, PMD, find bugs kind of static analysis. But it's more extensible, and you can use it on CSS and JavaScript and C. It is basically just a very clever Lexa parser with rules built in. I've started playing with this recently, and I'm slowly moving away from find bugs and PMD and finding myself writing more and more stuff in Freud. So, quick recap. Don't neglect your basic testing skills. They are far, far more important than your multi-threaded testing skills. If you haven't got the basics down, you will never get the more advanced stuff. Like I said, runners have all these issues with them. Rules are new, well, relatively new. Use them in preference to runners if you can. I wouldn't suggest going around and refactoring all your old code to get rid of the old runners, but just write new stuff with rules instead. And make sure you're focusing on what's most important to you, or most important to the quality of your software, rather. Don't forget to make sure that when you're testing real-world situations. There's no point testing something with 5 threads if it's going to run with 500. Likewise, there's no point testing your code with 1 million threads if you're only going to have 2 users. It's a waste of effort. Choreographing stuff, making sure it comes together, making sure that when you're testing threads that you're testing the correct interactions, the correct sequence of steps. Make sure that if you're using a shared resource, that you're watching for the critical blocks of code. You're making sure that if interleaving happens, it's not going to leave your application in a bad state. And of course, don't forget that there are more to Java's synchronization than the synchronize keyword. It's a huge topic, but yes, definitely check out the newer alternatives in the Java libraries and also outside. Once you know you've got a shared resource, then you will probably find that quite often that'll be reduced. You can reduce it to a two-threaded situation, like the producer-consumer with a shared queue. That's usually enough, but of course, if you don't think that's realistic, then you can't use Threadweaver because it only handles 2 threads. You have to use something like ByteMon instead. JPF, it might be worth having a play with because it does have some out-of-the-box stuff that you can just use. But before you invest a lot of time in it, I'd seriously recommend making sure that you're aware of the current project state and whether it's useful to you or whether something else that's more actively maintained would be better, like ByteMan. ByteMan, you probably guessed, I love ByteMan. I think it's brilliant. But use it sparingly. You know, it's not a golden nuclear warhead or anything like that. It's just another tool. It's not going to level the playing field for you. So yeah, make sure that you're spending your time wisely when you're testing multi-threaded code, because a lot of the time you can spend hours, days creating test scenarios for situations that are just not going to occur in your application in real life, or you don't actually know whether there's an issue there at all in the first place. So do make sure that you think before you code and that your tests are worth writing in the first place. These slides will be up on Parlay's and my website as well, so those links that just scroll past, you'll be able to get those. And we are now out of time. So thank you very much for my quick dive through multi-threaded testing, and if there's any questions, I think you probably better come talk to me down here after the talk. Thanks.